Good morning, everyone. Welcome to our Big Data Visibility Series Part 2. My name is Anna. I am your moderator for today. I will go over a few logistic items as well as introduce you to our speakers, and then we will get going from there. First off, you can enter your question at any time during this presentation into the question queue. We will, however, only address them at the end of our presentation, usually 10 to 15 minutes at the end. During the presentation, there will be an opportunity for you to participate in our vote. And post or during the presentation, you can also check out the attachments available in this webinar for further education as well as additional information about the series. At any time, you can always go back and view this webinar on demand, even after the event day up to 1 year from now. Without further ado, let me introduce you to our speaker today. I have with me Tony Zanoon and Adway Gupte. Tony and Adway, would you like to introduce yourself to the audience?
Sure, thank you, Anna. Good morning, everybody, and thank you for joining us today. My name is Tony Zanoon, and I'm the Senior Director of Security Strategy for VSS Monitoring, and here today to have a dialogue with our product manager for Big Data Visibility, Adway.
Hello, everybody. Thank you for joining. So I'm Adway Gupte, and I'm the product manager for, as Tony said, the Big Data Visibility push that VSS is doing right now. I'm happy to be here.
Well, thank you so much for joining us today. As I said, we want to have a dialogue, and this is a second part of a series. Many of you may have had a chance to see the first part that Andrew Harding presented about the high-level view of big data and why people are turning to big data infrastructures. We're just going to drill down a little bit more into that. If you haven't had a chance to take a look at it, I do suggest you go back and look at it and kind of see some of those high-level topics. We will try to review some of the key items. So what we're going to talk about today is about big data and what we think is the future of big data as it pertains to network monitoring. To do that, let's just talk about what is big data, right? And there's different definitions around that. For purposes of clarity, we're going to use Gartner's definition, which defines big data as data sets that customers are turning into, which has three attributes: high volumes, variety, and velocity. And our conversation is going to be sharing our thoughts around how network monitoring and big data infrastructures can be interlaced, and why we want to be, leverage some of the intelligence that network data can bring into your big data infrastructure. Having said that, let's take a look at the big data. We believe that the network data is a big data problem. As the sheer amount of data that's traversing your networks of the enterprises increases, it's becoming more and more difficult for existing tools to keep up. That's a very simple fact that everybody has realized as the velocity and the volume of data just growing at very rapid speeds. So what they're doing is they're adding more and more tools, which brings more expenses both on OpEx and CapEx. And big data visibility is a new network monitoring paradigm, the way we look at it, where network monitoring tools would become virtualized or decoupled, if you will, from the capture and analytics and work in a big data technology or infrastructure. The actual collection of the packets, we believe, will be offloaded to special technologies such as network packet brokers. Additionally, we think that bringing the network data into the big data stores will allow for correlation of contextual profiling, a level of intelligence into other part of data with maybe CRMs or Active Directory data, so you create a bigger contextual intelligence or situational awareness. Looking at big data, we have to realize that big data means different things to different people, and there's definitely different reasonings behind it. One aspect is, as we said, the sources of big data. What are the drivers? Whether it's business intelligence or business analytics, CRM, ERP, or social media, many have turned into big data to try to keep up with the attributes we talked about, the volume, variety, and velocity. There's also the level of granularity that infrastructure owners and IT or business are looking for when they turn into big data, whether it is looking at the metadata, whether it is going beyond that and take sampling, and what kind of a data you want. You want to look at all the aggregate data or every single cells on a daily or weekly basis. There's definitely going to be some use cases, and Adwa and I are going to be talking about it. We keep 2 or 3 to talk about and how we think this convergence is going to happen. And but in general, there's use cases around business intelligence, billing, marketing, insurance, customer loyalty, and obviously about architectures. So, Adwa, do you want to share some of the information that we're going to be leading into as far as the architecture aspect? What are some of the different architectures that we're going to be talking about today?
Thanks, Tony. So, as far as big data and bringing network data into that is concerned, or even in general big data, really, we're seeing 2 kind of main architectures where initially when big data came on the picture, people were storing data directly into the HDFS, and that's still a very valid way of doing things. But in some of our customers, we're beginning to see a shift towards storing the data into a centralized enterprise class solution, for example, the Isilon from EMC, and making the data available to Hadoop. So there are kind of different ways of where you store the data, either in HDFS or in a network attached storage or a storage area network, and make it available. But before we dive into the architectural details of things, let me just quickly go over a primer on what are the different network data formats, what are the ways in which you can represent network data. So raw packets, this is the network data format that's widely used right now. So what this consists of is the layers such as the NPV makes copies of each packet and sends them across to tools, and individual tools have to do everything from capture that packet, store it, analyze it, absolutely everything. So that's the existing paradigm. And then there are 3 more data types. There's PCAPs. PCAPs are an industry standard format of storing packet data or storing network data, where every byte is captured into a file along with a little bit more metadata, for example, the time of capture and the interface on which that data was captured. So that's one data type. The next is metadata, which is a slightly higher level of abstraction. So metadata is the standard definition of metadata is data about data. So it's a higher level of abstraction. It doesn't have absolutely every byte that was transmitted, but has the important pieces of information. And finally, there's flow statistics. These are now aggregated at the level of flows, where the definition of flow varies from organization to organization, but the most commonly used one is the communications which have the same source IP destination, source IP port numbers, source destination port numbers, and the protocol. Those are classified as one flow, and then we have statistics which are aggregated at that level. So what we see happening is that the raw packet format is going to kind of get phased away as we go forward into the future, and PCAPs, metadata, and flow statistics, which are ways of representing the network data in a file which can be stored, are the ones which will be the data types of the future, because these can be stored and then analyzed by big data technologies such as Hadoop, and we're going to be talking about the different ways in which these can be used. So now we've talked about 3 different data types, and each of these is good and bad for different kinds of use cases. So before I dive into each of these a little bit, let me just talk about what they're good for. So PCAPs, they're great for historical intelligence. So every byte is stored. You can go back in time and look at what exactly happened on a given in a given point of time. So let's say you have a problem, a customer has a problem last Monday, and they call you up. You can go back at PCAPs and look at what happened last Monday and exactly figure out what happened. So that kind of historical intelligence PCAPs are great for. Metadata are a higher level of abstraction, and they're great for contextual intelligence. So, for example, PCAPs are going to tell you that IP address A was used to transmit a given set of bytes to IP address B. Metadata, on the other hand, will be a text file which will contain some of this information and then can be used to correlate with, say, the DHCP records to tell you that IP A was assigned to a given laptop. Then you can look at your authentication records to figure out that user X was logged into that laptop. And so you're basically able to correlate different parts of information using metadata to come up with a more complete picture of what happened on your network. And finally, we have flow statistics. So as I said, these are aggregated at the level of flows, and they are great for forming patterns and establishing baselines. For example, you could establish the baseline amount of TCP traffic or UDP traffic on your network, or for example, DNS traffic on your network, and then any departure from those baselines can be easily identified. So each network format has its own pros and cons, and it's used for different things. So let's dive a little bit deeper into each of the network formats before we move on. So PCAPs. Now PCAPs are an open industry standard format. They provide a complete representation of network data. Everything that happened on the network is in the file. So this works well in scenarios where you don't know what information contained in your packets might be useful to you going forward. So those are the pros. But on the other hand, the problem is that PCAPs represent a huge amount of data. So for example, a 10 gig link is going to produce a gigabyte of PCAP in every direction each second. So if you're talking about a fully utilized bidirectional 10 gig link, we're talking about 2 gigabytes of PCAPs being produced every second. And that's a huge amount of data, especially as we move from, say, 10 gig to 40 gig to 100 gig. The other problem with the PCAP format is the format in which it is stored. So as you can see on the slide there's a global header, and then there's a packet header for every packet data. And the packet header contains the length of the packet that follows that header. So the problem with this is, in order to access the nth packet, you need to actually look at all the n-1 packets before that to look at the packet header, figure out the length that you need to skip over, and repeat this procedure. So random access is difficult, and that's a problem for PCAPs in general, for general processing as well as for specifically processing in Hadoop. Next up, we'll talk about metadata. So the metadata represent a higher level of abstraction than PCAPs. So rather than store every byte that traversed your network, metadata only stores the specific pieces of information that you identify as important. Also, metadata is a sort of loaded term. So metadata can mean different things to different people. One definition of metadata is data about data. So, for example, things that are not in your packets but can be gleaned from them, for example, the round-trip delays or the latency, the jitter, so on and so forth. Another definition of metadata, or another way of looking at metadata, would be if you look at the data that's being transmitted in the payloads on your network as the actual data, then the headers that are slapped on top of it to make the routing of that data easier in your network, or possible in your network even, that can be looked at as metadata as well. So regardless of which definition of metadata you use, metadata can be used for a variety of purposes. For example, let's say a security analyst is looking for a DNS tunneling exploit. Now, metadata can be used in this instance because you can look at specifically the port number, which would be 53, and the size of the packets, and you can start processing the metadata and look at all the port 53 packets which were larger than a certain size, or larger than the normal baseline. So for example, if your network has normally seen 100 byte DNS packets and suddenly you're seeing 1500 byte packets, then that's probably indicative of a problem on your network. The con of metadata is obviously that you need to pre-identify information that if you've not identified something is important to begin with, then going forward you will not have access to that information. And then finally, there's flow statistics. So this is the highest level of abstraction as far as network data formats are concerned. So flow statistics are aggregated not at the packet level, but at the level of the flows. As I covered earlier, the most common definition of flow is the 5-tuple, and the flow statistics are going to contain information such as the flow started at time X, ended at time Y, how many bytes were exchanged between these two endpoints, so on. So now, flow statistics were actually introduced in the form of NetFlow by Cisco, and the Cisco routers can produce these flow statistics as well as other routers, and they have different names, S-Flow, J-Flow, so on. But the problem with generating flow statistics on a router is that they're not the core function of the router. So whenever the router is overloaded with traffic, it's going to have a performance problem and it's going to stop generating flow statistics. So along came these specialized tools, which generates only flow statistics. That their only purpose of existence is to look at the packets on your network data and generate flow statistics, and those are the ways in which you can generate flow statistics. Now, an example of using a flow statistic would be, for example, if you're trying to proactively detect problematic events on your network. You can use flow statistics to generate a baseline for your network and then identify departures from that baseline. So the DNS tunneling exploit that I talked about earlier in the metadata slide, you could do that, use the flow statistics as well, because you're looking at, say, 1% of your network is normally used by DNS. Suddenly you're seeing 25% being used by DNS. That's a departure from baseline that you should probably investigate.
Thank you, Adwait.